Hello everybody. The reactions we have studied so far involved electrons which are outside the nucleus. Now in this chapter on nuclear chemistry, we look at changes that affect the nucleus. So first, let's discuss about radioactivity. Let's discuss about radioactivity. Okay, so some substances such as uranium, they spontaneously emit active invisible radiations. So these radiations, they affect photographic plates, they ionize gases, or they penetrate solid matter, and also they excite luminosity in substances like zinc sulfide. So such substances are said to be radioactive, and the phenomenon is known as radioactivity. So spontaneously emission of active invisible radiations. So we call radioactivity as spontaneously emission of active invisible radiation. Now the nature of radiations depend on the type of material and the type of conditions that we are getting into. So for example, nature, it consists of positively charged helium nuclei known as He2+. So these type of nuclei emit alpha rays. So whatever elements emit helium nuclei as a part of a reaction, we call that element is undergoing alpha emission, and the rays that are taken out, that are given off by the elements, we call them as alpha rays. Okay, and their electric charge is 2 units positive charge. Their mass is 4 AMU, just the mass of helium nucleus. So let's discuss about something about these type of rays. So let's say this is alpha rays, this is beta rays, and there is another type of rays emitted known as gamma rays. Okay, so the nature of these type of rays we will be studying about electric charge, about mass, and about ionizing power. And the other properties are not so important, but still it is advised that please go through other properties like relative penetrating power, or speed, or the action on ZNS photographic plates, because anything can be asked. Anyways, so we'll discuss about speed as well. So the nature of alpha rays is that it consists of positively charged helium nuclei. It consists of electrons, and it consists of electromagnetic radiations. Gamma rays consist of electromagnetic radiations. Okay, and now electric charge, it's 2 units positive charge. In this case, it is 1 unit negative charge. Gamma rays, they are neutral. They are just electromagnetic radiation similar to X-rays, but they have very much shorter wavelength. Mass of alpha rays is 4 AMU, as the mass of helium nuclei is 4 AMU. In this case, the mass of beta rays is same as that of mass of an electron, which is 1/1837 AMU. As we know that mass of one electron is around 1/2000 AMU, or to be exact, it is 1/1837 AMU. And gamma rays, they have no mass. They have no rest mass. Okay, so the ionizing power of alpha rays is quite high. It is quite high. Whereas in case of beta rays, since we know that kinetic energy equals half mv square, therefore their kinetic energy is very low because of very small value of mass, and hence their ionizing power is small because of low kinetic energy. And gamma rays, they cause ionization but in an indirect manner, that is secondary effects. We are not going to study these type of, but just know that they cause ionization. They cause ionization indirectly. Okay, so the speed of alpha rays, it varies. It's about 1/20th to the speed of light. It is 1/20th of speed of light, or velocity of light. Whereas in case of beta rays, it's around 3 to 99% of velocity of light. But in case of gamma rays, it's equal to the velocity of light, as we know that electromagnetic radiations, they travel at a velocity of light. Therefore, they are equal to the velocity of light. Okay, so the relative penetrating power for alpha rays is very small. If we say that the penetrating power of alpha rays as 1, then the penetrating power of beta rays will be 100, and that of penetrating power of gamma rays will be 10,000. For alpha rays, it's quite small because of large mass and small velocity. Therefore, they penetrate only very thin aluminum foil. Whereas in case of beta rays, they have more penetrating power because of smaller size and high velocity, and therefore they can penetrate about 2 millimeter to the aluminum. Now, electromagnetic radiation, needless to say, their penetrating power is very, very high. This is because of high velocity and non-material nature. They can penetrate considerable distance of even dense matter. Okay. So, there are several theories of radioactive disintegration or theories of successive transformation, and there are mechanisms of radioactive change. So, a radioactive change is accompanied by small decrease in mass. Remember this fact that a radioactive change is accompanied by a small decrease in mass. Okay, the lost mass appears as an equivalent amount of energy carried by alpha or beta particles and frequently by gamma ray photon. Therefore, it has been shown that elements with atomic number greater than 83 are basically unstable. Now, let's discuss about alpha ray change or alpha change. So, let's discuss about alpha ray change. Now, when an alpha particle is ejected from a radioactive element, the product or daughter element has 2 protons and 2 neutrons less. Okay, since alpha particle is He2+. Therefore, this is ejected in case of alpha ray change. This is ejected. So, helium nucleus of mass 4 units and charge plus 2 units are ejected from any alpha change. Okay, and the products are known as daughter elements. Now, this means that product will be placed 2 places to the left of parent element. Just we can see it through an example. Suppose uranium 238 uranium undergoes alpha change, then this process will be shown like this. 238 uranium gives us 234, since there will be a decrease in 4 units in mass, atomic mass, and there will be decrease in 2 units in atomic number. Therefore, there will be 90. So 90 to 34 shows us that the element is thorium. Plus helium will be given out. So alpha decay produces isodiaphers, that is, parent and daughter nuclides have same difference of number of neutrons and protons. So they produce isodiaphers. Isodiaphers means that any two elements which have same difference of number of neutrons and protons. So the difference is neutrons minus protons are same. They are same in case of isodiaphers. Okay. So let's study beta change. So whenever beta ray change take place, when a beta particle is emitted, beta particle means an electron is emitted, a neutron in the nucleus is converted into a proton and an electron through a sequence of changes, and the electron is emitted as the beta particle. So therefore, in this case, an electron is emitted as a beta particle. So the example is, suppose 234 thorium, it undergoes a beta decay. So it will produce 234 of atomic mass. The atomic mass will not get changed, 234, but since electron is getting ejected, therefore there should be an increase in atomic number. So this arrangement corresponds to this element. So, and hence we write here the process of beta decay as this. Now these two elements, 90Th234 and 91Pa234, they are known as isobars. That is, they have same mass numbers but different atomic numbers. You must have studied it. So it produces isobar. It produces isobar. Isobar is produced. So in case of beta decay or beta change, isobar is produced. Now positron emission. Positron is similar to that of electron. It has no mass, or the mass of 1/1837 AMU, but the charge is positive on positron instead of negative on electron. So in case of positron emission, this species is eliminated. Okay, so this is eliminated or emitted. For example, if you take here, you can write as proton. For example, this proton, which undergoes neutron, produces a neutron plus one positron. Contrary to beta change, where in this case a neutron undergoes a proton plus electron decay. For example, in case of beta ray change, similar to this, here proton is undergoing dissociation as neutron and positron. In this case, a neutron undergoes dissociation as a proton and an electron, and electron gets ejected. So here positron gets ejected. So the example here is nitrogen. 13 and 7 undergoes as 13C6 plus 1 positron. Okay. Now there is another another concept of radioactivity, K electron capture. Generally, this is shown in, or this is studied in more detail in when someone studies X-ray. So this type of mechanism is exhibited by X-ray. Now, in certain nuclei, the nucleus captures an electron from the K shell. Now, because it is nearest to the nucleus, therefore it will capture an electron from the K shell. The vacancy created is filled up with electron from the higher shells, and therefore they emit X-rays. As a result of K electron capture, a proton in the nucleus is converted into a neutron. So whenever suppose a proton is there in the nucleus, and whenever an electron goes inside the nucleus, or if it is captured by the nucleus, then these two meet to form a neutron. Hence atomic number decreases by 1 unit. Therefore in this case atomic number decreases by 1 unit. Okay, remember this fact. So there are many examples for this. So one of the example is here, this element barium plus, whenever an electron is captured, it undergoes as cesium 133. So atomic number has been decreased by 1 unit, atomic mass remaining the same, plus X-ray is emitted. So in this case X-ray gets emitted. Now there are many theories to say that the stability of nuclei is there or not. Okay, so there is one theory known as N/P ratio theory. So in case of N/P ratio theory, so when the number of neutrons were plotted against the number of protons, it was found that the stable or the non-radioactive nuclei lie in a well-defined belt called the stability belt. And it was found that generally the nuclei of those atoms are stable whose ratio of neutrons to protons lie in the range of 1 to 1.5. So according to N/P ratio rule, the nuclei of those atoms are stable whose ratio of the neutrons to protons lie in the range of 1 to 1.5. Okay, so for example, calcium is considered to be one of the most stable nuclei. It has atomic number as 20, mass number as 40. Therefore number of protons here is, in case of calcium it is 20, number of neutrons in case of calcium is 20. Therefore N upon P equals 1. So now there are other theories as well to decide the stability of nucleus. So the other theories are even, odd even, and odd nuclei. In this case, elements with even atomic numbers usually have greater number of stable isotopes than elements with odd atomic numbers. So there is another theory as even, odd theory. So in this case, elements with even atomic number usually have a greater number of stable isotopes. Greater number of stable isotopes than elements with odd atomic numbers. Then elements with odd atomic numbers. Okay, so this is another theory for to determine the stability of nucleus. There is another theory known as magic number theory. In case of magic number theory, nuclides with magic number of protons or neutrons, that is either of 2, 4, 20, 50, 82 or 126, they are particularly stable. So we need not discuss this theory because this is not confirmed. Moreover, that theory is not applicable everywhere. Okay, so in chapter on chemical kinetics, we discussed about rate of radioactive disintegration. As if you must remember that rate of radioactive disintegration on kinetics, in the chapter on chemical kinetics, since we know and we discussed that all radioactive decays are first order in nature. Therefore, here rate is minus dN upon dt equals lambda n, where lambda is disintegration constant or decay constant. Okay, and the negative sign shows that the decrease in the number of atoms of that particular species is taking place. So from here, if we solve this equation further, we get the rate equation as, or this implies us that lambda equals 2.303 upon T log 10 n upon nt. So this n naught is the initial number of atoms and nt is the total number of atoms left at time t. Lambda is decay constant, t is the time that has elapsed. So from here, half-life period is 0.693 upon lambda. This is a constant. Therefore, T half for a particular radioactive decay is constant, and it equals 0.693 upon lambda. There is another concept known as average mean time, and the average mean time equals 1 upon lambda. So from here, we can say that T half equals 0.693 into T average. Okay, or from here, average lifetime equals 1.44 into T half. So from here, average lifetime is greater than that of T half lifetime. So the radioactive series are the periodic table the periodic table is arranged in radioactive series known as thorium series or uranium series or actinium series. So thorium series is denoted by 4n. 4n series. Uranium series is 4n plus 2, and actinium series is 4n plus 3 series. So in case of thorium series, the mass number of all the members are divisible by 4, whereas in case of uranium series, mass numbers of all the members when divided by 4 give the remainder as 2, and in case of actinium series, these give the remainder as 3. So in case of thorium series, 6 alpha and 4 beta particles are emitted. They are emitted, Whereas in case of uranium series, 8 alpha and 6 beta particles are emitted. In case of actinium series, 7 alpha and 4 beta particles are emitted. Okay, so this was the concept about radioactive series. Now, there is a term known as radioactive equilibrium. This is nothing not so important to be discussed, because if you have very clear understanding of concepts, then by using chemical kinetics you can calculate when radioactive equilibrium takes place, and the units of radioactivity, these are in becquerel or in curie. So each unit is interconvertible into other units. So let's discuss about artificial or induced nuclear reactions. Now, radioactive isotopes of ordinary stable elements such as phosphorus and nitrogen are produced by the collision of a moving particle called as a projectile. Suppose here, in case of induced radioactivity, now since we know that here if we do something like this transformation, P15, it gives us 30 Si14 plus 1 positron. Okay, so the radioactive isotopes of ordinary stable elements such as phosphorus here, they are produced by collision of a moving particle called as a projectile with a nucleus, referred to as target, and the radioactivity of such elements or such radio elements as 30P15, which are produced artificially from stable isotopes of other elements. Now this process is known as artificial radioactivity. Okay, so radioactivity produced artificially are called artificial or induced radioactivity. Okay, so now from here, another name of induced nuclear reaction or this type of induced radioactivity, this is known as transmutation, for they change or transmute one element to another. Since they change or transmute one element to the other, they are also called as transmutation. This process is also called as transmutation. This process is also called as transmutation. Now there are certain characteristics is that proton gives us neutron plus positron, because a positron gets ejected while transmutating one element into another. So there are many methods of transmutation. It may be by alpha particle, or it may be by protons or deuterons, or it may be by neutrons or anything. So let's discuss about nuclear fusion. This is an important part of this chapter. Nuclear fusion. Nuclear fusion. So a nuclear reaction in which two lighter nuclei are fused together to form a heavier nuclei is called nuclear fusion. A nuclear reaction in which two lighter nuclei are fused together, to form a heavier nuclei is called nuclear fusion. So in this case, a deuterium and a tritium, if they are fused together, suppose to initiate a fusion reaction, although it is very much difficult, but once it is started, continuity is maintained due to large release of energy. A very huge amount of energy is released in this case. And for this reason, this is also known as thermonuclear reactions. They are very much highly exothermic in nature because loss of mass occurs when heavier nuclei is formed from two lighter nuclei. Examples may be, suppose here 2H, one that is deuterium plus 2H. 2 deuterium is forming helium plus it is giving out 24.9 mega electron volt of energy. Suppose 24.9 mega electron volt. This is very high energy indeed. Okay, and here one hydrogen, when it fuses with 3 hydrogen, it gives out one helium or one alpha particle plus 20 mega electron volt of energy. So suppose the energy units when two atoms are colliding, they are forming the energy of units of mega electron volt. This is indeed very huge amount of energy considering if we take it to molar level. Okay, so now there are various advantages of fusion reaction because it's giving us huge amount of energy, and the advantages are that it is abundant fuel supply. It is in abundant fuel supply. There is no air pollution. And there is no high level nuclear waste. There is no high level nuclear waste. Okay, now let's discuss about nuclear fission. Nuclear fission. Here, by definition, it is a process of artificial transmutation that we have discussed just now, in which heavy nucleus is broken down. In this case, heavy nucleus is broken down. It is broken down into two lighter nuclei of nearly comparable masses. Which release a large amount of energy. That's why nuclear fusion and nuclear fission are used in very high level processes, because very huge amount of energy is released. For example, if uranium undergoes nuclear fission to 235, if it undergoes bombardment with a neutron, it undergoes nuclear fission giving us barium 56.39 plus krypton, which is 9436, plus 3 neutrons, and plus huge amount of energy. Here. Okay, so now in addition to above reaction, there are various side reactions occurring also. Various side reactions occurs. For example, uranium, it forms xenon and strontium, and it also forms xenon and strontium plus 5 nucleus, 5 neutrons. It forms 2 neutrons. So one fission reaction, if it gets started, it can cause other fission reaction. Okay, so here xenon, it undergoes beta emission as cesium. Now cesium further undergoes beta elimination as barium. Okay, now it undergoes further beta emission as lanthanum. Now this further undergoes beta emission as cerium. So see, you can see that once nuclear fission gets started, one fission can cause another fission. Therefore, one fission can cause another fission. Okay, so this is the case with nuclear fission. It has to be controlled at some point of time. This is known as chain reaction. So therefore, the chain reaction is self-propagating if the value of multiplication factor is more than 1. And multiplication factor is known as multiplication factor, or K. By formula, it is the number of neutrons produced in one step. Number of neutrons produced in one step divided by number of neutrons produced in preceding step. Produced in preceding step. So whenever the value of multiplication factor is more than 1, the chain reaction takes place and it is self-propagating. Okay, so there are various types of uses of nuclear fission and nuclear fusion. The greatest use is in the form of fuels. As we all know this, that a very small amount of material can give us very high amount of energy, since we have seen here and here, since they are giving us very high amount of energy. Therefore, nuclear fuels are very much advantageous to us. And at the same time, there is a great disadvantage of this nuclear fission and nuclear fusion reactions, and they are in the form of atomic bombs. And that is why their use needs to be controlled. So, now let's discuss some of the questions based on this chapter. So, in this question also, in this chapter also, majority of questions are asked from theoretical part only. The alpha decay, beta decay, what is nuclear fission, what is nuclear fusion. You must be acquainted with these facts, and also you must be acquainted with the kinetics of radioactive decay that follows first order reactions. So the applications include carbon dating. So all of these are the examples of first order reactions. So make sure that you are well equipped with all of these concepts. So let's discuss some of the numerical questions that can be asked apart from theory in NEET JEE. So the first question is, the half-life of 32P is 14.3 days. Calculate the specific activity in curies of a sample of phosphorus containing 1 part P32 per million parts of phosphorus. Atomic mass of phosphorus is 31 units, or there's 31 AMU or units. Okay, so To solve this question, we know that specific activity means activity per gram of sample. Okay. Now 1 gram atom of phosphorus equals 31 gram of phosphorus equals 6 into equals 6.023 into 10 raised to power 23 atoms. We know this from mole concept. So therefore 1 gram of phosphorus equals 6.02 into 10 raised to power 23 upon 31 atoms. Okay. Now, and hence in this case, in 1 gram of phosphorus, this much number of atoms are present. Therefore, 32 phosphorus present in 1 gram of the sample equals, just divide by 1 upon 10 raised to power 6, that is divide by 1 million, because it's given in the question it contains 1 part per million. Okay, so this equals 6.02 into 10 raised to power 23 upon 10 raised to power 6 into 31 atoms. So the amount of 32 phosphorus in 1 gram of sample is this much number of atoms. Now activity, we know that activity equals K into N. And since the value of K equals 0.693 upon 14.3 into 24 into 60 into 60. So we have done this just to convert the units into dps per gram. Therefore, K is nothing but the rate constant or decay constant or integration constant or lambda, whatever you are most comfortable to call it. So into 6.02. So K equals this. So therefore, activity equals Kn equals 0.693 upon 14.3 into 24 into 60 into 60 into 6.02 into 10 raised to the power 23 divided by 10 raised to the power 6 into 31. So this is the activity of the sample. So activity comes out to be, from here it comes out to be 1.089 into 10 raised to the power 10 dps per gram. And since this activity is in per gram, therefore we can say that this is also the specific activity. Specific activity, it equals 1.089 into 10 raised to the power 10 dps. And if we convert it into Curie, because the question in question it is asked that the activity that we need to calculate specific activity in Curie, therefore if we to convert it into Curie, we have to divide it by 3.7 into 10 raised to the power 10. So therefore this equals specific activity equals 1.089 into 10 raised to the power 10 upon 3.7 into 10 raised to the power 10 Curie. So from here specific activity comes out to be 0.294 Curie. So this is the answer. Okay, so another question. Let's discuss another question. The question asks us that the nuclei ratio of 1H3 to 1H1, that is, this is tritium. This is tritium to hydrogen in a sample of water is 8 into 10 raised to the power minus 18 ratio 1. Tritium undergoes decay with a half-life period of 12.3 years. How many tritium atoms would 10 gram of such a sample contain 40 years after the original sample is collected? Okay. Now for tritium, since half-life is given to be as 12.3 years, therefore for tritium lambda equals 0.693 upon 12.3 per year. So from here we get the value of lambda as 0.05634 per year. Okay. Now since the proportion of tritium in the sample is extremely small, therefore the molar mass of sample may be taken as 18 gram per mole. Okay, that is the molar mass of water. So since the proportion of tritium is very small, so therefore take M equals 18 gram per mole. That is the molar mass of the sample. Now the number of moles of H2O in the sample is, therefore the number of moles of this H2O in the sample is, it equals 5 upon 9 into 8 into 10 raised to the power minus 18. So from here we can say that this equals 5 upon 9 into 8 into 10 raised to the power minus 18. 5 upon 9 from, since in the question it is given to be as 10 gram, how many tritium atoms with 10 gram of such a sample, and since molecular weight is 18, so 10 upon 18 comes out to be 5 upon 9. So 5 upon 9 into 8 into 10 raised to the power minus 18. So this is the number of moles. Therefore number of atoms of 3H1 atoms equals 5 upon 9 into 8 into 10 raised to the power minus 18 into Avogadro number. So if we substitute the value of Avogadro number, then number of atoms comes out to be 5.353 into 10 raised to the power 6. Let's take it as initial number of atoms, that is N naught. And since the time is given to be as 40 years, therefore lambda equals 2.303 upon T time, that is 40, log 5.353 into 10 raised to the power 6, that is N naught upon N, that is time at which, that is total number of molecules after 40 years. And since the value of lambda is 0.05634, and hence from here we got the value of lambda 0.05634. Now if we substitute the value of lambda in this expression, then we get log 5.353 into 10 raised to the power 6 upon N equals 40 into 0.05634 upon 2.303. So this equals to 0.97855. So from here 5.353 into 10 raised to the power 6 upon N is antilog of 0.97855. So this antilog comes out to be 9.518. So from here value of N is 5.624 into 10 raised to the power 5. This is the required number of tritium atoms after 40 years. 5.624 into 10 raised to the power 5. Okay, so let's discuss one more question, and the question is very small. It's asking us to fill in the blanks. Okay, here this question can be solved by the law of conservation of mass as well only. So when a uranium is bombarded with a neutron, so we studied about nuclear fission, nuclear fusion, and nuclear fission about type of reactions. So this is a type of nuclear fusion. Okay, so this in this case, if conservation of mass is taken care of, then we can say that atomic mass of the given species should be 2. It is lagging by 2. Atomic number is changing by 0. Since there is no such species, atomic number should be changed by 0. Since there is no such species, therefore it gives off 2 neutrons. Okay. So if you know about nuclear fission and nuclear fusion, we have discussed it just a while ago. You can answer this question very easily. And the second part is nothing but, since change in atomic mass is 0, therefore atomic mass should be 82. And change in atomic number, that is atomic number has been decreased by 2 here. Therefore if we equate both of the atomic numbers, both of the sides of the reaction, then here it should be 36. Now this corresponds to krypton. So this answer is solved here. This question has been solved. So very easy problems were there, and it was asked in IIT JEE 2005. Okay, so let's discuss another question. And the question says that a positron is emitted from 23 and A11. The ratio of atomic mass and atomic number of the resulting nuclei is. Now, one positron emission from nucleus, proton converts into neutron, therefore atomic number decreases by 1. So when one positron is emitted from nucleus, proton converts into neutron. So since we know that in case of positron emission, proton converts into neutron plus positron here. Okay. So in this case, atomic number decreases by 1, but atomic mass remains constant. Therefore, atomic mass is 23. It remains constant, but atomic number is decreased by 1. Therefore, atomic number decreases by 1, that is atomic number is 10. And hence, ratio of atomic mass and atomic number is atomic mass upon atomic number is equals 23 upon 10. So this is the answer. And this question was asked in IIT JEE 2007. Such an easy problem. Okay, so let's discuss one more question. And the question, it says that bombardment of aluminium by alpha particle leads to its artificial disintegration in 2 ways. One, that is here, and 2, as shown. Products X, Y, Z respectively are. We need to find what is X, Y, Z. Okay, so when this, when first part is taking place, suppose when this reaction is taking place, so aluminium here 27 Al 13, it is bombarded with an alpha particle which has atomic mass of 2 and number of atomic mass of 4 and number as 2. This undergoes, when this undergoes silicon 14, so this will give there should be, in order to balance the atomic masses, there should be 1 as atomic mass, and to balance for atomic number, here also it should be 1. So therefore this proton is our X. Therefore X equals 1p1, that is proton. Okay, so X has been solved. Now in second part, since aluminium is undergoing a bombardment like this, alpha 4 2, now it's giving 30 15. Okay, so in this case, in this type of transmutation, to balance for atomic mass, there should be 1 as atomic mass, and since atomic number is already balanced, there should be 0 as atomic number. Therefore we can say that this is neutron with no charge and 1 atomic number. Okay, so therefore Y is neutron. Okay, and now the third part, 15p30 4 2. Oh sorry, this is not the case. Now 15p30, now it is undergoing a change as 30 Si14. Now since atomic number is or atomic mass is already balanced, therefore there is no mass. And in case of charge, to balance this charge there should be plus 1 here. And we know that in this case this is a positron. Therefore Z here is positron. And hence X is proton, Y is neutron, and Z is positron. So very easy problem. This appeared in IIT JEE 2011. So very easy problems are asked from this question. Just make sure that your grasp on concepts is very good, and study chemical kinetics so that you can answer question based on radioactive reactions, because they all follow first order reactions. So and also study good about nuclear fusion and fission, and about alpha, beta and gamma decay. So that's all for this chapter. See you in the next chapter.